probably easier to go back and forth here.
Go.
Oh, we on?
We are on.
Hey, all right, and welcome back to Fabulous 8.4. Remember, you can find these online. Feel free to donate money through PayPal. Just kidding. So we're going to do 8.4 and 8.5, but this was one last problem that we're going to do on 8.4. Awesome. So data set 4 in Appendix B lists, this is our problem, lists a sample of 106 body temperatures having a mean of 98.4. Assume the sample is a simple random sample and that the population standard deviation sigma is known. When we hit these on the final, that's going to be your key. You have a bunch of different problems. This is going to be your key. You know that it's the mean, and you know that the standard deviation. Boom. So we know we're in the z-chart. To be 0.62. Use a, this is going to tell you that it's a hypothesis test. Use a 0.05 significance level to test the common belief that the mean body temperature of a healthy adult is equal to 98.6. We're testing that claim. We are testing that claim. So the first thing is, let's write down what that claim is. So, welcome to the workshop. It's over here. Awesome. So we're going to test our claim. I'll read it again to you. Use a 0.05 significance level to test the common belief that the mean body temperature of a healthy adult is equal to 98.6. Mean, we use mu, is equal to 98.6. Hooray! It's 98.6. The direct opposite of that, that's what we need. The direct opposite of it is mu. Think. What's going to go there?
Does not equal.
Does not equal to. That's the direct opposite. 98.6. Here's the fun part. Everyone likes the matching game, so let's match them up. Which one has the equal sign? Boom. That one. That one comes over. U equals 98.6. We were testing, this was our claim. Sorry, we had to put that on there. That was our claim. We're testing that mu equals 98.6. So mu equals 98.6. The other one is our alternative. Mu is not equal to 98.6. Aha! Where did our claim go? Our claim is in the null this time. I think it was in the alternative last time. So it can go either way. So here it is. The mu is in the, our claim is in the null. That's step one. Put that on here. Step one. Aha. Step two that we've done before like this. Step two, we've got to find the null and alternative are the critical values. We already found the null alternative hypothesis. We need the critical values in the critical region. So what we have from our problem is we have a significance level of 0.05. 0.05. That is great. That's what we need to know. So notice we have it down here. Alpha equals 0.05. So if we come back over this way, we have alpha equals 0.05. Aha! But is this one-tailed or two-tailed? And where we have to look to ask this is right there. If that is less than, it's one-tailed. If it's greater than, it's one-tailed. If it's not equal to, it's two-tailed. Two-tailed. So we're going to split this up. Well, I don't like to be stingy one way or the other, so I'll split it evenly. And that'll be 0.05 over 2, which equals a very common one, 0.025. And you can look that up in the chart, as we've seen before, but you already know it. It is negative 1.96 and 1.96 because we are dealing in a z-chart. And we are dealing in the z-chart because we know sigma. Okay. Perfect. Hey, we've set up the critical regions and the critical values. That's what we've done so far. The next step that we'd like to do now is this is step 2 and 3. We're going to go on to step 4 and find our test statistic. Yeah. Our test statistic. That's z equals x bar minus mu divided by sigma divided by the square root of n. That is our test statistic every single time that we're looking for a mean and we know sigma. Or sigma. So now we need to roll back over here to the problem. and we will find out what our sample is. Because we need to take a test. We tested it. We took a sample of 106 body temperatures, having a mean of 98.4. Aha! N is 106, and the mean is 98.4. Next up, though, we also needed to know sigma, so I'm just going to put these on there when we get over there, but sigma is the standard deviation known to be 0.62, right there. So if we come back over here, we know that x bar was 98.4 minus mu, which we assume to be, from our null, 98.6 divided by the sigma, which is 0.62, divided by the square root of n, which is 106. I'll give you some time to do that in your calculator, or you can hit pause, and I will stop. Like that.
Hit stop?
No, you don't have to hit stop. Okay. So, hopefully what you got for that answer was negative 3.32, which of course, we all know that z is the number of standard deviations
away from the mean.
Away from the mean, perfect. And we say that's darn high, but remember our critical values can move around, so we still need to test it, but negative 3.32 is not going to be usual very often. And sure enough, it's not in this case. We plot it over here in step 5. That's negative 3.32. It looks to be in the critical region. There it is, and sure enough, it's in the critical region. Since it's in the critical region, what do we do?
Reject.
Reject. What do we reject?
The claim.
The null hypothesis.
Oh.
We always reject or fail to reject the null hypothesis. Then we ask where the claim is. So you're right in this case. We're going to go reject the null hypothesis, which means that we do indeed reject our claim. The evidence does not support the null hypothesis. The evidence does not support our claim. Thus, the evidence does support the alternative. So there's various ways you can write it. I'm going to say the evidence does not support the claim that mu equals 98.6. You could write more about that. In fact, what we found is that the evidence suggests that normal temperature is not 98.6. Does it mean that that normal temperature isn't 98.6? Doesn't mean that we've proven anything. But this test suggests, keyword suggests, this test suggests that the mean temperature of humans is not 98.6. Doesn't say whether it's higher or lower, but it does say, even though this suggests that it's lower, but it does, our test says that it's not equal to. So there we have it. Okay, next up we're going to do 8.5, which is the same exact thing, except we don't know sigma. And just like in confidence intervals, if we don't know sigma, we can't use the z-table like we've been using so far. Only difference is we're going to use the
T.
t-table. We're going to use the t-table. See you in a minute.
Yeah.